My name is Benjamin Martin, and I'm with Tucker Vecchio and Adam Finley, and we're presenting our Intro to Computational Math project titled Predicting Health Insurance Premiums using Linear Regression in Python. Our research question is, which individual factors have most influence on health insurance premium costs? While this may seem like a simple question, is actually one that affects millions of Americans every year. Health insurance is one of the biggest financial burdens families face in the United States, and what most people don't realize is that health insurance are quietly using your personal characteristics, your age, weight, and whether you smoke or not, to calculate exactly how much you're going to pay. And they don't tell you which of those things matter the most. Before we get into the data, let me give you some context for why this matters. First, pricing transparency. Insurance companies set premiums based on individuals' characteristics, but they don't publicly disclose how much weight each factor carries. So someone can be paying thousands of dollars per year, but without really understanding what caused that cost. Second, smoking is a massive driver of healthcare costs in the United States. The CDC estimates that around $300 billion annually is charged to Americans for smoking costs. Because of this, the Affordable Care Act, the ACA, has allowed insurance companies to charge up to 50% more on their premiums. This policy is a big part of what we expect to see show up in our data. And third, why machine learning? Traditional linear models are useful, but they have limitation, and they can only model factors at one at a time, assuming each independent is in real life. No factors. A smoker who has a high BMI isn't just paying for smoking plus BMI. It's a combined effect. Machine learning, especially artificial neural networks, can capture those kind of nonlinear patterns. And so this all comes together for our primary source, which is from our 2022 paper by Kash et published in the International Journal of Environmental Research and Public Health. Our data. Our data. So our data came from Brett Lamps machine learning with R on a Kaggle publicly data set with 1,300 we're estimating 1,300 records. Our data set included 6 different factors from age, BMI, number of children, sex, smoking status, and geographic region. And where we were charging going after the most is our charges. And from that, from the total insurance charges, it came 13,000 was the median was 9,000, and the maximum insurance cost was 63,000.
Hello, my name is Tucker Fetko, and I'm going to start by going over the data pre-processing in the 80-20 split. So before we could run any models, we needed to prepare the data. We did this in 4 steps. Step 1 was checking for missing values. We confirmed that all 1,338 exact records were complete. No gaps, no nulls. Clean data is essential for reliable results, especially in something as precise as this. Step 2 was encoding categorical variables. Our model can only work with numbers, so we converted things like smoking status into binary. 1 for smokers, 0 for non-smoker. Sex, region, and other categorical variables were handled very similarly. Step 3 was z-score normalization, which we specifically needed for our AND model. The idea is that if one variable is in the thousands, like insurance costs, and another is 0 to 5, like number of children, the model will unfairly weight the larger numbers. Normalizing scales every feature to the same range, certainly centering at a mean of 0 with a standard deviation of 1. Our fourth and final step was the 80-20 train test split. We used 1,070 records to train the model and held back 268 records to test it. This is a standard validation technique that many data scientists use. The whole point is to see how well the model performs on data it's never seen before. A model that only works on its training data isn't actually useful in the real world. Moving on to the mathematical models. Now let's get into the math. We built and compared 2 models. First, a multiple linear regression, and secondly, an artificial neural network. Starting with multiple linear regression, or MLR, it is a more traditional approach. The model predicts insurance charges as a linear combination of all our values. So y hat is equal to beta plus beta age and less, and such. Each beta coefficient tells you how much that variable contributes to the predicted premium. The coefficients are estimated using ordinary least squares, which minimizes the residual sum of squares. The total squared difference between what the model predicted and what the actual values were in the matrix forms that close the form solution is beta is equal to xtx to the negative 1 times xty. The advantage of the MLR are that it's fast, interpretable, and the coefficients are easy to explain. The downside, however, is that it assumes all relationships are linear and it can't model interactions between variables. That's where the artificial neural network comes in. Our AN uses a feed-forward architecture with an input layer, one hidden layer, and an output layer. The forward pass through the network looks like y hat is equal to w sub 2 times f of such, where f is the ReLU activation fund. That's just max 0z, which introduces nonlinearity into the model. The weights w sub 1 and w sub 2 are learned during training, meaning the network adjusts itself to fit the pattern in the data. The key differences from LLR is that AND doesn't assume linearity. It can model complex interactions like the combined effects of being a smoker and having a high BMI, without us having to specify that relationship in advance. The trade-off is that it's less interpretable. You can see what the model predicted, but it's harder to exactly explain why. Moving on to our code. Here's a quick look at a snippet of our code. On slide 8, you can see how we computed, or sorry, excuse me, on slide 7, you can see how we computed the 5-number summary for our numerical variables, age, BMI, children, and charges, using pandas. This gave us the baseline statistics I mentioned earlier. On this slide, we generated the distribution histogram for our insurance charges. You can clearly see the right skew here. The vast majority of people are clustered at a lower charge amount with a long tail extending towards $60,000. This visualization helped confirm our understanding of the data before we moved into modeling.
I'm Adam Finley, and I'm just going to quickly talk about our key findings. So our first and most significant finding was that the smoking status is the single most influential factor in determining health insurance premiums. Smoking in our dataset paid a mean annual premium of $32,050 compared to just $8,434 for non-smokers. That's a difference of roughly $23,600 a year. You can see this clearly in the bar chart. The average cost for smokers is nearly 4 times higher than for non-smokers. This is a direct reflection of the ACA policy that allows insurers to charge tobacco users up to 50% more on their premiums, and it confirms the primary finding from our source, Cauchy, that smoking status is the leading predictor of insurance costs. So our second key finding is that BMI is the second most influential factor in premium pricing. Our MLR coefficient for BMI show that for every one unit increase in BMI, the predicted annual premium goes up by $335.78. The correlation between BMI and charges was 0.198, which means the relationship is real but moderate. Not as dominant as smoking, but still clearly meaningful. What's interesting about the scatter plot in this slide is how it breaks down by smoking status. You can see that for smokers, represented by the blue dots, there's a steep upward trend as BMI increases. The line climbs sharply. For non-smokers in orange, the trend is much flatter. This suggests the combination of smoking and a high BMI has a compounding effect on premiums. It goes beyond just adding the two factors together, exactly the kind of nonlinear interaction that our ANN was designed to capture. Some more model results. So we'll see how these two models performed. We evaluated them on 3 metrics: R squared, mean absolute error, and root mean squared error. The MLR model achieved an R squared of 0.7833, meaning it explained about 78% of the variance in insurance charges, with a mean absolute error of $4,186.51 and a root mean squared error of $5,799.59. The ANN model outperformed MLR across all 3 metrics, reaching an R squared of 0.8274, an MAE of $3,423, root mean squared error of $5,177. So the ANN is explaining about 83% of the variance and is on average nearly $760 closer on its predictions than MLR. That improvement comes directly from the ANN's ability to model nonlinear relationships and variable interactions, which MLR fundamentally cannot do. So quickly talk about a few of our limitations, because they matter when interpreting our results. First, our data set is small. 1,338 records is enough to run our models and get meaningful output, but it's a tiny fraction of the 310 million insured Americans who have in 2024. Our larger data set would almost certainly improve our accuracy there. Second, our location data is too broad. Our data set divides the country into just four regions: Northeast, Southeast, Southwest, and Northwest. But insurance costs vary dramatically within those regions. For example, New York City and rural New Hampshire are both in the Northeast, yet their insurance markets are completely different, so our regional variable does not carry much analytical weight. Third, our privacy limitations. Our dataset does not include detailed individual information. Things like specific health metrics or personal history are not included and does limit what our model can access. And fourth, finally, our missing key factors, real insurance companies have access to individuals' full medical histories and pre-existing conditions, which heavily influence premiums, and we don't have that information, so our model should be understood as informative estimates, not definitive predictions. In conclusion, our project set out to answer which individual factors most influence health insurance premium costs, and here's what we found. Smoking is number one. Smokers spend estimated $23,600 more per year on average than non-smokers, largely driven by the ACA's 50% surcharge allowance. BMI is number two. Every single unit increase in BMI adds roughly $335.78 to their annual premium. And the ANN is a more accurate model, outperforming our MLR in all three metrics, due to its ability to capture nonlinear relationships between variables, and making it a better predictor. Ultimately, these findings are useful not just academically, but to give everyday people insight into what's actually driving their healthcare costs and highlight areas where behavioral changes could have real financial impact. Thank you.
You know,